Hello everyone. By now you have done basic terminology about functions. Now in today's session, we will be talking about equality of functions. Now before even introducing this, I'm just thinking that does it occur to you that functions can be equated? Like in previous classes, you were dealing with numbers. Now slowly I introduced you y equal to fx, where x is a variable. I don't know how many of you have noticed, but I kept saying that x can take different values. F applied on it keeps giving you values of y. That means y is also a variable, x is also a variable. So slowly our journey is from numbers to variables. Now understand this thing, that our human mind tells that whatever I have done by now or whatever I have learned by now, I would try to apply it to next. So keeping that in mind, I am saying that how many of you thought that if I could equate two numbers, can I equate functions? So yes, we can equate functions, and answer you would get in this session. Now when do we say two functions are equal? We say two functions are equal if their domains are same and fx equal to gx happens for all x. Every word is important. I have written there for all x. So please do not attempt of just comparing fx and gx, fx equal to gx for some values of x, and then conclude that two functions are equal. No, fx equal to gx must happen for all x, and also the important condition is their domains should be equal. Domain is heart of the function. Without domain you cannot work. So otherwise also, whenever you are a given function, you must understand what is its domain, and if required, be ready with range also. Range is not required here for equality of functions. Now, let me take example. I take example where fx is given to be x upon x square and gx is given to be 1 by x. And question is, are functions f and g equal? Now, fx is x upon x square and gx is 1 upon x. The thing is, the moment you see something in the denominator, your first question should be, are they defined? So what are the values for which f and g, these two functions, are defined? Okay. Are they defined everywhere? No, they are not defined at x equal to 0. And hence, x equal to 0 will have to be removed from their domains. And luckily, both the functions do not have x equal to 0 in their domains. So we realize the domains of f and g both is nothing but R minus singleton set 0. So at least their domains are equal. Now what is left to be seen? That is fx equal to gx. I realize that fx is x upon x square, and since I have already mentioned that in its domain x equal to 0 does not appear, so I am free to cancel that x. Cancelling means you are dividing. Okay. So it is nothing but 1 by x. And 1 by x is same as gx. So what we have found is fx equal to gx, and we have also found that domain of f and domain of g, they are equal. So the final answer should be the functions f and g are equal as their domains are equal, and fx equal to gx for all x is happening. Now let us go to next question. And the next question is, now my f and g are x square upon x as fx and gx equal to x. Fine. Now again same idea, that we will check their domains and we will check if fx equal to gx is happening. What happens is that I say x square upon x is x for fx, and that is same as gx. So fx equal to gx may happen. But what about their domains? Are domains equal? The thing is, gx does not have any problem because it is defined everywhere. So domain of g is R. And what about domain of f? Since x appears in the denominator, we will have to remove x equal to 0 from set of real numbers for its domain. So R minus 0 is the domain of f. Now since their domains are not equal, so f and g are not equal. One question I have taken where f and g are equal, and one question I have taken where f and g are not equal. I think this should give you good idea that how to compare two functions. Let us move further. Next part, which is very, very important to us, is algebra of functions. Because the moment you have compared now functions, your next question could be, can we add two functions? Can we subtract one from other? Can we multiply two functions? And so on. So the first thing is f and g are two functions and both are defined from R to R. Then first rule is f plus g or f minus g. This is name of the function now. You may call it h also. F plus g, f minus g when applied on x gives you fx plus gx or fx minus gx. Mind you please, fx plus gx or fx minus gx would appear in the codomain part, and f plus g would be name of the function, or even f minus g would be name of the function. So it was intuitive for us that f plus g on x or f minus g on x will produce fx plus gx or fx minus gx. Now next is product of two functions, that is f dot g. Dot I have written for the product. F dot g applied on x gives me answer fx into gx. Mind you please, f dot g is name of the function. Fx dot gx would be value of the function f dot g. I hope it is clear to you. Now if product rule is available, then why not quotient? For quotient also we have a separate thing. F upon g applied on x produces fx upon gx. But the moment I write gx in the denominator, realize that gx can be 0 also. So we will have to add their condition provided gx not equal to 0, just to be safe. Now one more, which is actually combination of two functions I am saying. One is taking absolute value and function f itself. Absolute value of f applied on x gives me answer absolute value of fx. You know what? That right hand side absolute value of fx you have seen before also, like absolute value of 2x plus 3. So in place of fx I am writing 2x plus 3. But we have never seen actually the left hand side. This is theoretical, that left hand side appears as absolute value of f. But right hand side we have seen n number of times. Now these four things are comparatively easy to understand. But the next what would follow looks complicated. I am not scaring you, but I am telling you with all sincerity that whatever would follow here onwards, you will have to understand every small word or every small thing. I mean, do not neglect anything. Next is that we go for maximum of f and g, and that is defined as f plus g plus absolute value of f minus g whole divided by 2. Now this I have written only in terms of names of the function. Actually, you all must be thinking that is this the name of the function? I mean, such a big name. Okay, let us apply on x and see how it works. That maximum of fx and gx I would like to find, and that is obtained as fx plus gx plus absolute value of fx minus gx whole divided by 2. This becomes the formula now. Now, you may by heart actually, from examination point of view, this maximum or even next one which is going to be minimum, they keep appearing in competitive exam. So it's better that you remember the formula. So minimum of f and g is f plus g minus absolute value of f minus g whole divided by 2. Now again, it's better or we are more comfortable if I write in terms of x. So I write minimum of fx and gx, and that is fx plus gx minus absolute value of fx minus gx whole divided by 2. These last two, they look little scary, but please don't get scared. Keep revising them and then you will get hold on those two formulae. Now let me take one quick example so that you will have some relief. And that example is based on exactly of maximum of fx and gx, where fx is given to be x square and gx is given as x. And we have to find maximum of fx and gx. One way could have been that you draw graphs, which right now I have avoided because I wanted you to understand importance of that formula, that how to apply. But otherwise, one option I can also give you, that you try to draw graphs of fx and gx on the same set of axes and then come out for the answer of maximum of fx and gx. Anyway, let us start with maximum of fx and gx. Write down the formula. What is fx here? X square. And what is gx here? X. Substitute that. And I get maximum of x square and x as x square plus x plus absolute value of x square minus x upon 2. And that x square minus x inside absolute value what I have written, I can also write as x into x minus 1. Now, quantity written inside absolute value notation must take my attention. Why? Because that can be negative, that can be positive. Recall what you have learned in basic algebra and try to apply here. Critical points are 0 and 1. They matter to us. And we realize that when I'll mark on the number line, we will get regions x less than 0, between 0 and 1 and greater than 1. So, there have to be 3 regions, less than 0, between 0 and 1 and greater than 1. What happens in the region x less than 0? That same thing happens in the region x greater than 1. That x into x minus 1 is positive. And between 0 and 1, when x takes values, between 0 and 1, the quantity x into x minus 1 becomes negative. So quantity written inside absolute value notation there, which is x into x minus 1, is negative in some part and positive in some part. So while removing absolute value notation, please take care and try to write the expression for maximum of x square and x. That I write in x less than 0 region and x greater or equal to 1 region. Answer will be same for maximum of x square and x. And that is x square plus x into x minus 1 whole divided by 2. So when you open it, you will get 2x square upon 2. That would be x square. And the interval 0 to 1, there I will get answer for maximum of x square and x as x square plus x minus x into x minus 1 whole divided by 2. So now when you simplify that, x square and x square will get cancelled and you will get 2x upon 2. So let us rewrite finally as the answer. Maximum of x square and x is x square when x is less than 0. Between 0 and 1 it is x, and for x greater or equal to 1 it is x square. Now it looks better definition instead of like the previous formula, the big one. I'm sure something you have learnt out of it. Revise more and more questions. Try, attempt more questions, and then you will get hold grip on the topic. For the time being, this is good enough. When we meet next time, I'll come again with something new. Till then, stay tuned. Bye. Thank you.